it's a pleasure to introduce you to Tim Dodwell, who is a senior lecturer in industrial applied mathematics with the Institute of Data Science and AI at the University of Exeter, and obviously a Turing Fellow. And he's going to talk about deploying reinforcement learning in safety critical systems. I don't know which ones, but we're about to find out. Tim, over to you.
Thank you very much. That's really nice. So hopefully everyone can see my screen. It's a new platform for me, which is exciting given the number of platforms I've done. So something to try out. So yeah, I think probably the talk I'm actually going to give, maybe I wrote that title a little while ago, is to tell you a bit about Project Bluebird, which is a large program which is really kicking off at NATS and Turing, which I am leading with my counterpart at NATS. And NATS is the National Air Traffic Service. And I guess the key idea is, or the question we want to pose is, can we build an AI algorithm that can control a bit of airspace? And that is a technical challenge, and it's a huge safety challenge for deploying AI data science in the real world. So before I go into the details, a bit about the program, how it's kicking off, some of the challenges that we're going to face in doing this. It's a good opportunity to tell you what NATS do. So NATS, the National Air Traffic Service, basically control all the planes above our head. And they are strongly regulated, thank goodness. So safety is an extremely high priority. But as you can see, the little picture below, the little traces you see are all the planes coming over from America in the morning towards the UK. And their job is to safely maneuver aircraft around the sky to get them to their destination, separate them safely, and ensure they do it as efficiently as possible. And due to COVID-19, that's been a bit of an easier thing to do recently. But at the peak, managing traffic was around 8,000 flights a day. So a really technically challenging safety critical problem, with a concentration obviously around the southeast of England, around Heathrow and Gatwick, making it a very dense area of air traffic. So super challenging. And so the question posed is, it's industry which is under huge pressure in terms of being more sustainable. It's heavily regulated, it's safety. Can we design AI agents that can control a piece of airspace, that can remain safe, but do it in a more efficient way to ultimately reduce the sort of environmental burden on the aircraft travel causes in our environment. And so to summarize what's important to NATS, their primary target is about safety. But the second target really is long-term. How do we increase, be able to cope with the increasing aircraft? And that could be standard aircraft or the future, how do you deal with drones, autonomous taxis, etc. So an increase in infrastructure, but also be more sustainable. I think NATS came to Turing to develop that partnership to sort of fundamentally see if AI can do that and start addressing the challenges which that sort of crops up and take advantage of the opportunities. So this is funded by the government. So it's an EPSRC prosperity partnership, which I'm really happy to lead. And yeah, so the big aim is deliver the world's first AI system to control a piece of airspace. And that's an ambition I wrote down as an academic. And then NATS caused NATS to sweat, thinking, what would we actually have to do to actually make this a reality? So it's an extremely ambitious target. And it includes a diverse range of people, academics from different backgrounds, which I'll talk about, and partners across the Turing network. So Exeter, where I am, and also Cambridge University. So really good example of a sort of national Turing program with a really important sort of transport infrastructure in the UK. So the program only recently kicked off, so we don't have huge outputs to say, but really it's a nice opportunity for talk about the vision, about what we foresee as the challenges and the areas of which we're focusing on, and I welcome anyone to give suggestions or ask questions around it. So the themes that are split up are between what we call a digital twin or a probabilistic digital twin of UK airspace, and machine learning control, and then safe and explainable air traffic control. So the first part, a probabilistic digital twin for UK airspace, is really at the moment the predictive models about, okay, this is the current state of aircraft at the moment. What will it look like in 1 minute, 5 minute, 10 minute, an hour's time are deterministic models. And they have actually physics-based models about how aircraft will behave in the future. But what they're really interested in is not only about a prediction, but also around the uncertainty of what might happen. Because if you're going to have to make safety critical decisions, actually you want risk associated it. And risk means quantifying what possibly could I see in the next 1 minute, 5 minute window to be able to sort of strategically make decisions about safety. And so our first part is to take a unique data set from NATS. So they have all 20 million flight records for the last 15 years, all weather data across the UK. And how do we take that data and learn a probabilistic representation of air traffic flows? And that's a really exciting data science problem, a challenging problem. And interestingly, in the mean, so most of the behavior we see, we can predict well from historic data. But actually, there's interesting questions that there hasn't been an aircraft crash in the UK in the last 15 years. And as a data scientist, that's, a challenge, because we now, in the things that we're trying to protect against, we don't have data about the rare events that we want to do. So how do we combine observable data that we have, lots of data which we see every day, patterns of behavior, but maybe physics-based models that when we extrapolate beyond things that we've observed, we can still make good predictions of what might happen. Really interesting challenge. The middle part, machine learning control, is how do we then build an agent to control a piece of airspace? And this is a really exciting problem. The strategies we've been looking at the moment are optimization-based methods, so dynamic optimization-based methods. And also there are possibilities in sort of advancing reinforcement learning methods to look at this challenge. But I think, there's lots of open questions in reinforcement learning, and initially sort of more classical optimization methods are a challenge. But one of the challenges we're facing at the moment working with NATS in the optimization activity is, how do you define success? I mean, what is good, and how do you define a metric for that? And so we call this sort of designing the reward function in these methods. And that's a really nice example of close collaboration with industry about, we need to understand what defines good and how do we then recreate that in the mathematics which we deploy. And I think the first two are all, doable programs. But I think the biggest challenge we'll ultimately have is, how can we be provably safe? And how can we be explainable? So it opens up huge questions. So if an algorithm gets it wrong in controlling space, who is ultimately responsible? These will be systems that will be integrated alongside humans. So how do you design algorithms that work in sympathy with a human controller rather than detract from them? So the classic one is that if an AI agent takes over 95% of the control and it leaves only the risky situations to a human, do they lose situational awareness? And we have teams looking at psychology of, how do you design an algorithm, how do you design the visualization of an algorithm to assist a human rather than actually make the human more risky. And so lots of interesting questions coming up, and ones that not only don't apply to air traffic control, but broadly apply over many areas. So I think a really fun thing about this project, as I've hinted, is we have a really diverse team, and something that only a national institute could bring together. So that not only academics, but software engineers, and then the NATS team, so the research, the engineers in NATS. And this then also, even in the academic team, obviously it's lots of flavors of academics. So I'm an applied mathematician and look at Bayesian statistics and modeling. We have people interested in optimization. We have psychologists. We have people in computational ethics. So a real opportunity to take, a sort of big national view about how we tackle these problems for such an important partner in the UK and bring them together. So I think it's a unique thing about Turing and the project we're working in. And some of the things that we think are important and we're working on. So at the moment in controlling air traffic, there are no open benchmarks. So actually using data set, and interesting you're saying about synthetic data. So in the last program, that, can we take NATS data, build synthetic examples which are representative, and then provide open benchmarks so the AI and machine learning community can start tackling these problems. This hasn't been done yet. So I think in terms of an applied field, they're missing a trick of all the clever cookies in applied maths and AI, which would love this as a problem to tackle. A really exciting area is two-way training. So a couple of weeks ago, I was actually put through ATCO training, air traffic control officer training, and I was put in a simulator. And it wasn't real airspace, but I controlled a piece of airspace. So that was an exciting opportunity for me, but also having people from NATS teaching them about data science, increasing their awareness of what's possible and what's not possible with AI is a big part of the program. Working with regulators, obviously heavily regulated industry. So how do we communicate with them? How do we make them part of the journey so that what we come up with is a sort of missable solution to this? A really interesting challenge and one faced with many problems. And then the final, sort of building a UK network in ATC and in air traffic control is a really nice output. But one thing I would point to is we're trying to embed what we call the Turing way. It's a project in Turing about ways of operating. So, how industry works with a slightly manic professor to solve a problem, looking at ways that we can get the most out of people in teams to work together. How should we share information? How we should share data, and sort of lessons learned. So it's a program that we're learning a lot from in Turing, but also trying to use this as an example of a diverse team, but a complicated program by which we can sort of learn lessons in how to do this well. I think I'm probably fairly quick on time, and hope that you can ask lots of questions. I was light on detail because we've only just started, but I really encourage you to ask the wackiest question you can think of about airspace and AI, and I'll try.
Thank you, Tim. And I have to say, quite coincidentally, you've combined two of my favorite things, basically aviation and Bayesian mathematics. So
okay.
If we didn't have to go for a break at some point, I would just keep you talking all afternoon. Luckily for you, we have actually had some questions already submitted, so you don't have to just listen to mine. I mean, somebody has asked, what are the main challenges? So I don't know if you can maybe point to 2 or 3 of the things that for you are the hardest about trying to apply your work to this field.
Yeah, I'll give you one from each of the themes. So the theme that I'm largely involved with is theme 1, which is about building a digital twin, probabilistic digital twin. And the hardest thing there is actually the bulk of the data comes from an area where it's not safety critical. You're just seeing normal behavior where it's fairly easy to control. So in terms of getting good predictive models in what I call the tails of distributions in unlikely events is difficult, because you can't do an experiment where you fly planes really close together. It just doesn't happen. So
good.
How exactly. It's a good thing, but it's a challenge for us. And then, so the interesting question is, okay, a plane obeys physics. So there's ways that, we understand about physics and we have data. And then how do you fuse this things that we know about physics so we can write down equations and the sort of absolute menagerie of data we have about airspace to try and be more predictive away from where we have lots of data. In the control situation, one of the hardest things is the unpredictable. So we have something called a dynamic state space. So we don't have a fixed number of aircraft that come into our space. So it's very dynamic. The number of aircraft coming in, one lands, so you lose a plane in your system, and then you maybe add 2 as 2 enter space. And being able to actually design algorithms that are robust to this is quite challenging, because lots of them are kind of set up so that they have fixed state spaces. So technically, an interesting challenge which we're getting over, which is good. But I think probably in the last theme is where actually, I think all the others are technical math challenges which are solvable and fun to solve. I think the real challenge is, in in society, actually, people are very afraid of aircraft, and safety is very pragmatic. So how do you make it provably safe? How do you get people to buy in that, you know, an algorithm that we write will be controlling airspace? And then how do you divide that responsibility for who's responsible for when something goes wrong? Or the explainability piece, an AI agent made an action, it resulted in an accident. Why did it make that action? And how do you unpiece that? And I think that can be, you know, by the nature of the methods, the huge data sets that we're using, tracing that back and that sort of explainability piece and trustworthy piece in a hugely safety critical industry is the biggest challenge, very much like any autonomous vehicles. Yeah.
And you know, interesting, that relates to, in fact, to two of the other questions that have come in. One of them is, how do you reconcile the black box nature of some AI with explainability? And the other one is, well, you know, will we actually ever trust AI to take control of our skies without any human intervention? So I think they're both related to what you were just saying, but is there an answer, or are these the main problems that you're working on at the moment?
So let me deal with the second one, because I think that's a bit easier. I think no, in the foreseeable future.
No.
And in a way, I hope not. So there are lots of applications where, so the ultimate aim of this is to have a live trial on a piece of airspace, but it'd be a very assisted trial, which humans, you know, really constrained and oversaw. So don't go panicking that you might be on a plane that's controlled by one of my algorithms in the next 5 years. But I would say that it has huge benefits to NATS. So they spend huge amounts of money training air traffic control officers. So having agents that can be assisted in their training that are realistic has huge value to make people better air traffic control officers. The other thing is, if I want to design a new bit of airspace to try and make it more efficient, I could test those designs out with by seeing how it is to control that piece of airspace with an agent that we've designed. And so it would be running it in sort of in a virtual environment to test out and design new pieces of airspace, which ultimately would then go in to make a more efficient system. So I always think that these AI agents will work alongside humans in the control aspect, but they have huge benefits even not doing the live stuff.
When you talk about designing airspace, presumably what you mean is that there are what to us are virtual pathways in the sky that aircraft use at certain heights and certain directions and so on, and that you might redesign that the way that you might redesign a road system on the ground. Am I getting that right?
Exactly. So airspace is split up into sectors, and really the size of the sector. So they tend to be smaller near Heathrow and then bigger away from it. And they're designed that a sector at the moment is controlled by a human air traffic control officer, and it's kind of the capacity which they can manage themselves. And they've inherited this structure from sort of 50 years of air traffic control. And then you might want to ask the question, well, are we doing it efficiently? Can we do it better? So you now design a new bit of airspace, and before sort of taking that further, I mean, embedding a new piece of airspace or changing how you sort of split airspace up it is a very expensive exercise. So you could put your AI agent and say, well, how does that deal with controlling it? Does it have issues? Have I just designed a system where all planes out of Heathrow and Gatwick are flying at each other and causing all sorts of issues? And so, it sort of becomes a test bed where you can sort of try and do better things and redesigning your airspace to be more efficient.
I hope you program in the odd pilot who goes, what? We've never done it this way before.
Apparently, so I thought it would be more adversarial, that you tell, like, I think I was thinking of my children, that you tell them to do things and there's either a substantial delay or they do exactly the opposite. But I've learned that, and probably technically we've seen more of a shift from reinforcement learning to optimization, because actually pilots are pretty compliant. So you tell them
I'm glad that pilots are more rational than your children. I mean, nothing against your children, but
no, I mean, I completely agree.
Anyway, enough from it. There's a couple more questions. Maybe we can fit one more in. So I'm going to arbitrarily choose. what applications could you see for your work outside of air traffic control? Where else could we apply it?
So another area that I work in, I mean, not air traffic control, but in design of composite aircraft, and sort of the steps that you need towards regulation of flying lighter aircraft, and sort of the challenges in designing methods that predict what might happen off the back of simulation and data when you don't get good visibility of the full system. And then you have to provide a sequence of evidence that, this will be safe, this will be deployable. So the sort of strategies, a lot of what you're doing in terms of getting people to buy into methods is about knowledge transfer. What pieces do I need within a program to say, I can convince someone that that the new methodologies that you're taking on are explainable, they're trustworthy, they're well tested. So core lessons learned about how you deliver complicated methodological algorithmic methods into safety critical systems. So generally, I think, autonomous vehicles, we've got a lot. So I think self-driving cars are ahead of the game in terms of how they're doing it. And a lot of funding is being pushed that. So I think we can learn a lot from them, but in a hope that we can also push back and pass on some lessons there. But I think, the nature of that problem is slightly different in the sense that there's not one central piece doing the control, that the control's actually with the individual cars themselves, and they're sort of finding their way through a system. Whereas here, I guess in a way, more easier to some extent because the control is centralized, right? So,
although of course, when we all have flying cars, there'll be too many of us, so you will have to rejig your system to deal with some kind of swarm engineering or something.
So it's interesting.
How long do we have flying cars?
Yeah, I mean, I think one. Well, yeah, I mean, I don't know the answer to that. You'd have to ask someone that's in the business. But I think what NATS are seeing now is they're moving to an unstructured airspace. So at the moment, they're designing airspace so that they do control a lot. But now, because they realize the type of vehicle that will be coming, is they essentially want to build motorways in the sky. So there's an agreement that a plane enters here and connects it there, and it's much freer for what the plane wants to do en route. And that shift to sort of freer airspace allows more flexibility and allows you to be much more efficient. But then you think, well, how should I design it so that it can be controlled to still remain, safe, as it were? So lots of questions.
Lots of questions. Thank you very much for telling us so much and yet raising so many more questions. And I guess people will have to come back to you and ask them on another occasion.